We come to the next presentation by Mr. Schmid.
Thank you.
The title of the presentation is Formation of Slip Bands in Nano polycrystalline copper sandwich between nanoscale brittle material.
Thank you, Mr. Chairman, for your kind introduction. So, I'm Dr. Schmid of Kyoto University. So, the purpose of my presentation today is talk about the result. We examine the fatigue behavior fatigue behavior of nanoscale polycrystalline copper, which is constrained by other brittle materials. Okay, so in this presentation, first, I'm going to talk about the basic fatigue mechanism of pure bulk metals. And I will explain the importance of our topic. Then I will show you the experimental procedure after that. So I will share with you some of result and discussion. And finally, so I will make a brief summary. Okay, so let me refresh your memory on basic fatigue mechanism in metals. When cyclic load is applied to metals, localized deformation constant region, which is usually called as persistent slip band, PSB, is generated. Inside the PSB, you can find ladder-like dislocation structure, which is formed by self-organization of dislocations. And the PSB, additionally, the PSB produce intrusion and extrusion on the material surface. It is known that the width of this fatigue substructure is approximately 1 micrometer, which is independent of material size. And it is also widely known that the PSB plays an important role in fatigue failure because the PSB acts as a preferential crack initiation site. By the way, the latest electrode devices contain a huge number of small metallic components with a size of less than 1 micrometer. Of course, fatigue becomes a serious problem when these devices are subjected to mechanical vibration or cyclic thermal stress. However, there is no space to form the PSB because the PSB is too big comparing to such small components. So we thought that such small metallic component with a size of less than 1 micrometer must possess characteristic fatigue behavior, which is different from that of bulk counterparts, or they don't show fatigue failure. So in order to examine that, in our previous study, we conducted cyclic loading experiment for the nanoscale single crystal gold specimen. The test section is located here, and this method utilizes resonant vibration. And in this experiment, we found the generation of intrusion and extrusion. And as you can see, the external appearance of this fatigue damage is very similar to the PSB in bulk metals. But the width was in nanoscale, and the formation stress was much higher than that of the PSB. This result demonstrated that such kind of very small components possess characteristic fatigue behavior. Also, in this project, as a next step, we focused on the fatigue behavior of a nanoscale polycrystalline metal, which is constrained by other materials. You know, there are very small electronic components in the electric devices, for example, metal line, usually polycrystal, and they are generally constrained by other materials. So in this case, the fatigue behavior must become more complex than that of freestanding single crystal with that strong deformation constraint. So in the experiment, first, we prepared multi-layered material in which copper and silicon nitride are continuously deposited on a silicon substrate. And this is a cross-sectional image. As you can see, very thin copper layer of which thickness is 200 nanometer is sandwiched between silicon nitride layer and silicon substrate. And in order to improve the interfacial strength between copper and silicon substrate, we inserted very, very thin titanium layer like this. And from these materials, we fabricated the specimen using focused ion beam. And so after the processing, we removed the damaged layer introduced by FIB by using the R1 ion milling. Okay, so this is the specimen we fabricated. The test section is composed of a silicon nitride layer, a copper layer, and silicon substrate. And this, the cross section of this test section has a trapezoidal shape. Since this specimen is oscillated vertically in this experiment, so this cross-sectional shape makes the stress level on the upper surface be higher than that on lower surface. So the fatigue damage preferentially appears on the upper surface. In other words, we have only to observe the upper surface to examine the fatigue damage. And the crystallographic information on the upper surface of the test copper portion was analyzed by EBSD. This is the EBSD map. And so this result indicates that the upper surface of CU portion is composed of 13 coarse grains. So we numbered these grains 1 to 13. And these are the stereographic projections of 13 coarse grains. And so the copper has a cubic, a face-centered cubic structure with 4 slip plane and 3 slip direction per plane, which gives a total of 12 slip system. So this projection, so the slip planes and slip directions are labeled A to D and 1 to 6 respectively on the basis of the Schmid and Bose notation. In this notation, the primary system, slip system, which gives the highest resolved shear stress, decided only by the loading axis and the crystallographic orientation, is expressed as B4, the combination of the slip plane B and slip direction 4. Okay, so this is an experimental system, and sine wave oscillation was applied to the specimen by controlling the input voltage to a piezoelectric actuator. And the deformation amplitude was measured by a laser Doppler vibrometer. And so using resonant frequency preliminarily obtained, we performed a fatigue experiment under constant deformation amplitude. In this method, if the fatigue damage appears in the test section, the displaced amplitude rapidly decreased because the resonant frequency is shifted owing to the change of specimen stiffness. So first, we applied a very small initial displacement amplitude to the specimen, and if there is no change up to 10 million cycles, we oscillated the specimen again with displacement amplitude that is a little higher than that previous one. And so if we find the rapid decrease in the displacement amplitude, we finished the test. Okay, so from here, so I will show you the experimental result. And this is the relationship between the displacement amplitude and the number of cycles. At the low displacement amplitude, the number of cycles reached to 10 million cycles, while the displacement amplitude remained constant. However, at the input voltage of 1.6 volt, the displacement amplitude rapidly decreased at around 50,000 cycles. And this is a frequency response curve. As you can see, after the input voltage of 1.6 volt, the peak was shifted. So from this fact, we judged the fatigue damage appears in the test section. And so we finished experiment. After the experiment, we observed a specimen surface carefully, and we found fatigue damage are composed of nanoscale intrusion and extrusion, which was generated by the activation of slip system B4 in grain 3. And this intrusion and extrusion had induced an interfacial crack by pushing the adjacent titanium layer. Like this. The formation of intrusion and extrusion plays an important role in fatigue interfacial cracking. And by the way, in the experiment, the nanoscale intrusion and extrusion were generated only in grain 3. So we try to explain this fatigue behavior from the viewpoint of Schmid factors. Schmid factors represent the anomalous resolved shear stress, which is decided only by the loading axis and the crystallographic orientation. As you can see, grain 3 does not have the highest value, despite the fatigue damage was generated in grain 3. So this means that the Schmid factors cannot describe this fatigue behavior. So as the next step, we decided to focus on the microscopic stress field, which is induced by the deformation constraint between grains and between dissimilar materials. The stress condition was analyzed by using finite element method analysis, which takes into account anisotropic elasticity of each grain. And the shape of grain boundary on the upper surface was reproduced on the basis of the result of the EBSD. Okay, so this slide shows the maximum resolved shear stress in 30 grain and its slip system. As you can see, the grain 3 has the highest value and its slip system is B4. Yeah, this result has a good agreement with the experimental. So this means that the characteristic fatigue behavior, which is introduced in the nanoscale polycrystalline metal, is governed by the microscopic stress field, which brings about by the deformation constraint between grains and so between dissimilar materials. Okay, this is a summary of my presentation. The nanoscale intrusion and extrusion are formed on the surface of grain 3 along the primary slip system. And nanoscale intrusion and extrusion induced interfacial cracking. And fatigue damage, very characteristic fatigue damage, was governed by the microscopic field and due to the deformation constraint between grains and between dissimilar materials. Thank you for your kind attention.
Thank you very much.